up here, please. Happy Wednesday. Go ahead and put your phones away. You don't need them out today. You don't need your computers out either, I don't think, unless you're taking notes on them or something like that. So Kimmy made that announcement this morning that got everybody's hopes up. I am pretty darn confident that I'm going to see you at normal Thursday time tomorrow. But I just want to remind you, the friendly reminder that if by some weird situation we are not here at all tomorrow, check your email after 9 o'clock in the morning and I'll send you something to work on, okay? As we know from Mr. Mueller, we don't have a lot of time to waste now, right? So we got to keep on cruising, keep on trucking. But I anticipate that we'll see you tomorrow. I'm just saying, but you know, whatever. All right, today we're going to do a quick rotational kinematics warm-up. We're going to work on Newton's second law with rotation. And then at the end of the period today at 2:05, who's watching the clock today? Who's got that clock watching? Who is? Eden is? Oh, it's okay. All right, Eden's got it. She's in charge. At 2:05, I just need a reminder that it's that time, and I'm going to get you those tests back. Today is, I think, okay, this happens every year, and every year I'm blown away by it. I don't know why. Abraham Lincoln, Charles Darwin, you guys know who those people are, right? Yeah, pretty famous, amazing people. They were born on the same day, like of the same year. I think that's kind of cool. I don't know. Anyway, just kind of messes with my brain a little bit. I think it's awesome. All right, here we go. Warm-up problem time. This is rotational kinematics. This is what we finished with yesterday, but you didn't get a chance to try it out. So here you go. Here's the situation. A bicycle slows down uniformly from a velocity of 8.4 meters per second to rest over a distance of 115 meters. Each wheel and tire has an overall diameter of 68 centimeters. There are 4 things for you to work on. I'm going to give you about 3 minutes. Everybody's got paper or a whiteboard out. You can work on whiteboards if that makes you happier. But either way, you need to work on this problem, get some answers, and then we'll discuss, okay?
Well, actually,
I don't want to necessarily regroup, but let's group. Okay, let's get started, and then if we need to take another work later, we can as well. Okay, let's just get started with where we're at. So a bicycle slows down uniformly from 8.4 to rest over a distance, blah, blah, blah. It says each wheel and tire has an overall diameter of this, determine these things. So let's just do part A, shall we? Just part A. Oops, more space here, please. There we go. Angular velocity of the wheels at the instant. How do we do that? So we could write down our givens. I'm just going to underline them because they're right here and because I want to move quickly. Angular velocity, what are we looking for? What's our unknown? Nope. What's our unknown, guys? Angular velocity. Look it up on your sheet. You guys, you should know this. And if you don't, that's why you have that bright gold staring in your face. What variable represents angular velocity? Omega. Angular velocity. Okay. We know the diameter, and if we know the diameter of the wheel, that means we know the radius. The radius is going to be what? It's going to be 34 centimeters or 0.34 meters. And if we don't know omega, but we know the radius and we know the velocity, can we find omega? Is there a relationship between those 3 things? Yes, there is, Miss Kay. We wrote it down at the end of the day yesterday. I wrote it down at the very bottom of my sheet, and I think you may have as well. Is there a relationship between omega, V, and R? What is it, Shushma? Bam, V equals omega times R. So solving that, we can get omega is equal to V over R. Yeah? We get a value? If you haven't done it yet, do it now. Omega is equal to V over R. V is 8.4 meters per second. R is 0.34 meters. It is really important that you have converted this to meters and not leave it in centimeters, right? Because you got meters per second here. Meters per second divided by meters What units is that going to give me something in? 1 over seconds or radians per second? Or hertz? It's all the same stuff. And what value did you get? 24.7? How we doing? Okay. Total number of revolutions. Did you get that one? Almost, maybe not quite yet. Didn't even start it. Do you need another 5 seconds? Okay. Okay, I'll give you another moment or two. Go, go, go. Needs to happen right now. So I think, my friends, many of you are either trying to rely on past experience in mathematics or something like that, which may or may not be a really good solid foundation. I don't know because I don't know what your experience was, okay? Or you are trying to make things just like round pegs fit into square holes, which doesn't work. My best piece of advice when doing rotation problems like this, first of all, is to take a step back, okay? And second of all, is to look at units. The units will tell you everything, okay? The units tell you everything. So I heard some people talking about 2 pi having to be involved. Why do you think that 2 pi has to be involved somehow? Okay, so 1 revolution, thank you, is 2 pi radians, right? Okay, so can we use that, or maybe even we can write it as something like 2 pi radians over 1 revolution? That's like a nice little conversion chart there, right? So we can actually use that for something, okay? What else do I need to know in order to solve this problem of the number of revolutions that it makes while coming to rest? What else do I need to know? Do I need the time? I'm going to go with the distance because I know that already. I don't have to do any other work. How far does it go? 115 meters, right? So we really want to figure out how many rotations 115 meters is. Do you know the circumference of the circle? You can for sure figure it out, can't you? Yeah, so 1 time around, the distance for 1 time around is what? How do you figure that out? 2 pi r. So that's going to be 2 times pi times, what did we say? So 30 or 0.34 meters. What is the circumference of that circle? Say it one more time. Thank you. 2.14 meters per revolution. And Chris, what are we going to do next? I feel like you're like there. You want to just say it. 115 divided by that number. And that might, excuse me, seem just inherently obvious to you. If it doesn't, that's okay. We can look at the units. If we do 115 meters and we divide that 115 meters by 2.14 meters per revolution, the meters on top and the meters on bottom, what are going to happen to those? They're going to cancel. What happens to the revolutions that are all the way down here? That's your unit because it's in the denominator of the denominator, becomes the numerator. So 115 divided by 2.14 gives you something like 53.8 or something like that. Well, it did. Here's 2 pi. Yeah, I mean, I wrote it out differently. So I wrote revolutions equals the delta theta divided by 2 pi. You can write it that way too. You can write it lots of different ways. But yes, in fact, we did use the 2 pi. For sure. Do you guys need another moment for C and D or no? Okay, I'll give you another moment. We don't have a lot of moments, we got a few. I'm gonna make this a little bit smaller so you have some space to look, some space to see it. Okay, I'm gonna give you a couple minutes. Go, go. Let's see if we can match something up here. All right, so for parts C and D, really this is getting back into the kinematics that we're going to use the guess method for, right? So we're going to write down our givens or write down what we know and then find an equation based on that information. So I'm going to go ahead and throw another space in here so that we can find the, nope, there we go, stop, here we go. All right, acceleration of the wheel. So that's our unknown, right? We don't know that, we don't know alpha. Oh, what do we know? What givens do we know to solve for part C? You know the final velocity, you want V or omega? Omega, right? We're going to do omega final, just because we're doing everything in rotation, so it makes the most sense. What is the final omega? It is. What's the initial omega? It is. Anything else you know? Okay, I heard lots of things, but I couldn't tell. Speak, somebody. Lucy, go. You can find theta, right? Yeah, yeah. So delta theta is, how do you find it? Yeah. So you can for sure find that. And that's a pretty helpful thing. Do you have an equation that has alpha, omega final, omega initial, and theta? Yes, you do. What equation do you have? Yeah. I'm going to just solve that for alpha because I'm lazy or something. Is that okay? Is that okay? Got to make sure to square stuff. Is the angular acceleration going to be positive or negative? It's going to be negative. Does that make sense that it's negative? Yeah, because the thing is slowing down. Yeah, it is. It's moving in a positive direction, but slowing down. What do we get for an answer, or for a value there? 0.9? Negative 0.9 what? It is. Yeah? Nice. All right, and then finally, part D asks for what time, how long does it take to stop? So you've got the same unknowns, or the same givens here. You're looking for time. I don't know if you remember when we were making lists of equations forever ago, that if you are looking for time, and you have omega initial, omega final, and delta x, there was that kind of hidden secret equation that you can use. The one that's the averages, you can use that one. So the rotational equivalence, so if you want to write this down on your gold sheet, you can. I will warn you that this one, again, is still not on the equation sheet, but you can absolutely use it. The equation that I'm talking about is, the equivalent is delta theta is equal to 1/2 omega final plus omega initial times time. Does that look familiar to you? The rotational equivalent of our translation equation. You can absolutely use this. Or you can use my favorite equation. No, it's not my favorite one. That's not the one I was thinking of. You could also use alpha is equal to omega final minus omega initial over time and just solve that for time. And use the alpha. Either way works. Doesn't matter. Did you guys get a value for how long this takes? 27.4. How we doing? Okay. So I'm hoping that going through this a couple of times and kind of seeing this, and there's some homework problems like this too, you'll see that it's the same stuff, just going around in a circle instead of going in a straight line. The problem-solving process is the same. The physics underlying it is all the same, okay? I want to go to the front of your gold sheet. We're going to fill in the next few lines today. We're going to do this as quickly as we can so we can do a few problems as well. So we're moving down to the second kind of big set of things. And right now, I want you to see how much of the translational side you can fill in for this chart here. So this is what I want you to fill in. Are these boxes, as much of them as you can. I'm just going to give you a minute to see if you can, and some of this is like you have to figure out what in the world I'm talking about, but see if you can figure out what is it that causes an acceleration and what units do we use to measure that? What is it that resists an acceleration? What are the units for that? And then you know how we like to write out Newton's first and second law? If this, then this, or if this, then this. Go ahead and give it a shot real quick. Then we'll regroup in just a sec. Okay, in deference to time, and because sometimes it's hard to read Miss Carbling's brain, I get it, okay? Let me tell you what I'm thinking here. Well, let me ask you if you can tell what I'm thinking. How about we'll try that? What causes acceleration, friends? A force. In fact, it's a what type do you have to have in order to have acceleration? I already started writing it. Yeah, some sort of net force, right? Net force not equal to 0, right? What is the unit that we use to measure force? Indeed it is. Hey, what do we measure mass in? In kilograms, always and forever. This is just a nice review of life, right? A nice review of physics life. And then you're like, oh man, I don't remember Newton's first and second law because we've been doing it. We haven't been saying it out loud, so let's do it right now. Here we go. Here it comes. If F net is equal to 0, what do you know? Indeed it is. Look at us. If F net is not equal to 0, then what? Acceleration does not equal to 0. And we can even put something a little bit more specific than that, can't we? We can say something a little bit more specific than that. We can say that the acceleration not only is not 0, but can you calculate the acceleration? Yeah. A is equal to what over what? Yep. F net over m. Oh, you forgot about it. This is a really great opportunity to remember it, right? This stuff is not going away. So it's good to have it. It's right there. This is all stuff you know and love. You understand. And now, today, we get to do the other half. So we're going to do this half over here. Here it comes. This is big deal stuff, you guys. Here it is. All right. You know this first part because we talked about the opposite. Remember way back a couple weeks ago when we were talking about Josh and TJ. Thank you for remembering because I don't. It was that a traumatic like it was okay. It struck a nerve. What was it that caused acceleration? That wasn't linear acceleration, but it was rotational acceleration. Do you remember what that was? That thing? What's that? A torque. Indeed. A net torque. And we haven't specifically articulated this yet, but what are the units? Or maybe we have, but we just haven't written it down anywhere. Newtons times meters, yeah. And I want to be very, very clear because you have seen the unit Newton meter before. We did it a number of units ago, and we actually called it something different. Does anybody remember what we called it? We did. We called it a joule. But here's the thing, and the reason I bring it up is because I don't want you to get confused. So full disclosure here, friends. What was the Newton meter joule business? What were we measuring? Do you remember? Energy and applying a force over a distance did what to an object? Starts with a W. Work. Yes. So here's the thing, and this is why it's really important. I want to tell you. You remember that when we did that, we had a force applying over a distance, and the force and the distance were parallel, right? And we were adding energy to a system, and so by doing that, we were applying a force over a distance, newtons times meters, to get a joule or some number of joules of work. There's a secret that underlies the definition of torque that is fundamentally different than work. Because for torque, the force and the distance from axis have to be what? Is it parallel? It's perpendicular. And there's actually some secret math that's in there, this thing called a cross product and a dot product that make these two things very, very different. And I'm not going to go into the details of that because you don't need it. But the reason I'm saying it is because I want to make sure that you recognize that torque is measured in newtons times meters or newton meters. It is not a joule, okay? So I want to just kind of like head that off right now so that you know. Thank you, appreciate it. I'm going to skip this middle line right here. I'm going to come down here because we've already established this one. What is the rotational equivalent to Newton's first law? What is it? Can you write it down for me? Yes, I can do that. Yes, you can. What is it, Eden? It's torque net. Yeah. If torque net is equal to 0, then alpha is equal to 0. The other piece of this, though, says if the torque net is what? Not equal to 0, then what? What do we know is not 0? Alpha is not 0. Dot, dot, dot. I'm going to say alpha is equal to something, but we don't know exactly what it is because we don't know exactly what this resistance to acceleration is. What's that? Counter torque. Good guess. No, it's not actually. Unfortunately, that would be kind of amazing if it was, but it's not. We're going to put a little box there. I am going to go back on my word, and I apologize to you guys, but I really want to fill this box in. So I'm not going to give you a test back today because it's just going to drive you nuts. And apparently, Lucy's okay with that. You did, but I want to go over the problems with you so you understand them. But I want to get this. So we're going to go down to the bottom because we're going to write something else down here. Okay? On the bottom of your chart before, you wrote this thing about converting from translation to rotational and back. We did a bunch of stuff with kinematics. We're going to do another one over here. And this one over here has to do with converting Newton's second law. So what I want to do is I want to start with Newton's second law as it's written in translational. So I'm going to start with F net is equal to mass times acceleration. Okay? And as you look, oh, hi. As you look at these things over here, what do you notice is kind of the common thread between converting from translational to rotational? There's a radius involved. Do you see that? Yeah. So just for kicks, because we can, we're going to multiply both sides of this thing by an R. Because why not? If you apply a force some distance, some radius away from an axis of rotation, what do you get over here? What's F times R or F times D? Been doing it for a while. What is it? It is. It's the torque. Absolutely. So this is a net torque. Now, instead of, I want to get like this M thing, we're not quite sure what's going on with that, but A, we know that there's a rotational equivalent. So instead of writing A here, I'm going to go ahead and write alpha times R. Because I know that A, the translational acceleration, is equal to alpha times R. So I'm going to go ahead and write it in there. So here, this is what's going to happen. We're going to go like this. We're going to say M times alpha times R times R. Are we doing okay? Oh, you're looking at me like I'm a little bit nuts, but I want to make sure that I'm okay. So I've got M times alpha times R times R. But you're going to tell me that R times R is just R squared, so that's not very like weird or different or whatever. So I'm going to write this as M times R squared times alpha because I'm just changing the order of things. I'm allowed to do that. So I've got torque net is equal to M times R squared times alpha. And then I'm just going to peek up here real quick and notice that in order to keep things nice and parallel and pretty, here I solved for A. So here I really want to solve for alpha. So let's solve this thing for alpha. So I've got alpha left on the right-hand side, and then I've got torque net over this weird quantity of mr squared. And this weird quantity
mr squared is in fact, like this is a big deal quantity right here, okay? This thing right here is essentially an object's resistance to a change in rotation. Rotational, I-O-N, I can't spell, T-A-T, yeah, I-O-N, okay? Okay, so I'm gonna scroll back up here, I'm gonna write this down. This first thing, alpha is equal to this thing, well it's, what was it? It was torque net over something. And I don't want to write that whole like mr squared business out. There's got to be a better name for it. Warning, this is one of the worst names in all of physics. Okay? It is, and I kind of wish, Chris, that you had been alive. I don't know how many years, like how many hundreds of years ago to have had events, you could have just coined that and used that forever. But unfortunately, there's this institutional term that we need to understand. And it goes back to the term that I've avoided saying here, and I use mass because mass is a better term, okay? But there's a term that starts with an I that a lot of people have sometimes used to describe things. I heard somebody say, who said it? It's okay, I'm not gonna scream and yell at you. It's just like a yucky term. It's not like a terrible term. The word was what? Inertia, right? But it doesn't mean anything, but this here, they use that kind of. So here's the goofiest term. I would rather have counter torque. But again, we have to live in the world of physics that exists around us. I like your revolutionary mentality. I love it, but unfortunately, I just, I don't know, man. I don't know if that would work. Here's the term. It's a 3-word phrase. I like one word. Counter torque sounds good. Unfortunately, again, we got it. Moment of inertia. Now, the term moment of inertia, all it means, you guys, all it means is an object's resistance to changing in rotation. Okay? So the bigger a mass is, the harder it is to accelerate translationally. The bigger an object's moment of inertia is, the harder it is to get it to accelerate rotationally. That's all we're talking about. That's it. Okay? That is it. Moment of inertia is marked with the letter capital I, which is weird. And I don't usually use that because I also, to me, means current, which is a whole different ballgame. We'll get there eventually. But you'll sometimes see it as I, whereas this one would be M. Okay. And the unit for it, well, excuse me, you can figure out the unit for it. What's the unit for it? Yeah, kilogram meter squared. How are we doing? Say again. It is T net over I, yes. Indeed. All right. Oh my goodness, are we okay? I'm gonna go ahead and show you a problem that we're gonna work on today, and we'll work on again a little bit tomorrow too. But I'm gonna show this to you. So this is a special bar that we have, okay? It's made of 3 segments of equal length, okay? They are drawn that way and they should be, but they all have different masses. The total mass of the bar is 6m, and the question says, this is gonna be kind of a thinker question because we don't have a lot of background to it, but I think you can do it. Will the moment of inertia of the rod be greater about the left end? So that means I'm going to hold on to the left end and rotate the thing. About the right end, and I'm going to rotate it, or the same. I'm going to hold on to it and I'm going to rotate it. No, I'm holding here and then I'm gonna rotate it up or down. Does that make sense? Like a door handle, yes. Okay? I'm gonna give you just a minute to take a look at that. Go. All right, my physicist friends, let's do it. What do you think? Did you come up with an answer? Yeah? TJ's shaking his head tentatively. Emma, how about you guys? Did you come up with an answer? Yeah? Yeah? Brady, what about you guys? Yeah? Okay, let's do it. Let's vote. So we've got either moment of inertia of the rod will be greater about the left end, the right end, or the same about both. So raise your hand if you think it's left. Bigger on the left. Bigger on the right.
I'm confused on why we're holding it.
So okay, so that's a really good question. And then or the same. I saw lots of for both of those. Let's make sure we understand the question. Shh, guys, I only have 4 minutes, so I really need your attention because I can't shout over you. Thank you so very much. So the question is, what do I mean by bigger? I mean, oops, I'm on froze. Freeze. Does the object resist to change more? So is it harder to get it started, and is it harder to get it stopped? Does that help a little bit? Okay. So is it harder to get it started on the left or on the right?
Wait, if you're grabbing it on the left.
If I grab it over here on the left,
It's gonna be harder on the right.
if I grab it over here on the right. Come here, Bo.
I'm confused. So it will be the. Yes, hit him with it.
No, I'm not gonna hit with anything.
Got it.
All right. So I've got a makeshift version of this. Okay, so I've got a meter stick with one weight on it, so it's not quite the same deal. But I'm gonna put it like this, right? Because then I've got the 3M here and the 1M here. So I should grab on this end and swing it up and down. Is it easy to do?
Kind of.
Okay, like kind now. Okay, whoa. All right, now come over to the other side, so it's the same way. I hope we don't break our meter stick. Don't break my meter stick, yo. Is it easier or harder?
It's a lot harder.
It's a lot harder. A lot harder means that it has much, what? More I. He says more I. When he's holding a larger moment of inertia, when he holds it where? On the left end, okay? I want you right now to write this down. I want you to draw a quick picture of that and take a couple seconds to write that down so you don't forget it. Because tomorrow is what we're going to do with that. What does it mean? Come here. You can feel.
Like, I know. What is it? It means like the greater the mass, the
This system has the same mass, regardless of if Bo holds it here or if he holds it here. But it's a lot harder to get it to move if he's over here.
So what are we writing down?
Same thing. So which way did you say, Bo, was harder? Moment of inertia of the rod will be greater about the left, greater about the right. What did you say? On the left, it is harder. Yes.
Well, actually,
So it's a greater moment of inertia. Yes.
no, wait.
Yes. Because the mass is further away from the axis of rotation. Ask your question, Shushu. No question? Yes question? Okay. Okay.